Good. I hope everyone had a good weekend. And so again, just to remind you, coming up this week due are your Chapter 5 homework and quizzes. And you're getting ready to take your second chapter exam. If you don't have one of these drawn on a piece of paper in your 3-ring binder, I would suggest you have one of these drawn. This will help you out tremendously while you're taking your exam. It just gives you a quick reference as to how to go about converting between units, grams and moles, between moles and particles, so on and so forth. And then there's some extras I have drawn here. On last week, we talked about molarity, and we said molarity is one of the more popular concentration units, and it is the most popular concentration unit used in chemistry. And so to convert moles to molarity, you simply divide by liters. And then to go in the opposite direction, to convert molarity to moles, you multiply by liters. And we said molarity is symbolized with the capital M, molarity being equal to moles divided by liters. And the moles are the moles of the solute, which is the part of the solution that gets dissolved. And the liters is for liters of solution, the total number of liters of the solution. And then we also learned in chapter 4 that we can use density as a conversion factor. So to convert between grams and volume, we can use density, and that's converting between grams and volume in units of milliliter, because density, symbolized with the lowercase d, is your mass divided by your volume. So therefore, mass will be equal to the density times volume. And so therefore to convert, and then again, volume will therefore be mass divided by density. And so with those relationships, then you can take mass and convert into volume by dividing by density. And then you can go in the opposite direction and convert volume into mass by multiplying by density. So this is a very good little conversion flow chart that enables you to do all of those different conversions that I just mentioned. And so again, your chapter 5 homework and quizzes are due Friday. Your second chapter exam will be due on Sunday, the 15th. It will cover chapters 4 and 5. And so on Thursday, after one of my sections of Chem 1010 lab is over at 2 p.m., I will have a meeting open on the team site. And if you have any questions about chapter 4 or chapter 5, or any concepts you need re-explained, or anything of that nature concerning chapters 4 or 5, Thursday at 2 p.m. will be a good time to drop in and ask your questions. And so I will send you an email to remind you of it. And I'll have, it will be the same team site that we're on right now. So the same link that you use to show on Monday and Wednesday, you'll use that same link Thursday at 2 to come to a question and answer session. And also, I'll be available Friday at the same time to do another Q&A session. So you'll have 2 opportunities to drop in and ask any questions you need to ask about chapters 4 and 5. And another thing that I'm going to do for you guys is I'm going to put together a little data sheet for the exam, and it'll include one of these flow charts and any other formulas or equations that we use to do calculations in chapter 4 and 5. I'll include that as well. And of course, you're going to need a periodic table that you're comfortable with, that you'll want to have downloaded and printed before you take the exam. So again, I'll email you reminders about the Q&A sessions that are going to happen at the end of the week. And so I would start looking through the chapters and marking up my notes and of any concepts and questions that you feel you need to ask more questions about, or you feel, hey, I want to see another one of those types of problems worked out. Things of that nature. Make you a list of questions and then just drop in at 2 o'clock on either Thursday and Friday. And feel free to ask any questions that you have on chapters 4 and 5. So when we ended class on Wednesday of last week, we had some questions that I asked you to look at over the weekend and work out. And I kind of gave you some starting points of how you would want to go about approaching these questions. The first question, they gave us a concentration in units of parts per billion for the mercury 2+ ion. And we need to concentration those convert those parts per billion units into units of molarity. And again, as we stated, molarity is moles per liter. And so we also discussed last week that a part per billion is the same thing as 1 microgram per milliliter. So if we have 16 parts per billion mercury ion, that means we have 16 micrograms per milliliter of that ion. So we need to convert 16 micrograms per mil into molarity, which is moles per liter. And so you first want to convert the micrograms into grams. And then once we get the micrograms into grams, then we're ready to convert those grams to moles, and then convert the moles to molarity. So using this little flow chart, it kind of gets us set on a pathway for how we need to approach solving the problem. So we weren't given grams, we were given micrograms, but by knowing our metric system conversions by prefix, then we can easily convert the micrograms into grams because 1 times 10 to the 6, 1 million micrograms is equivalent to 1 gram, or we can say 1 microgram is equivalent to 1 times 10 to the negative 6 grams. Either one of those conversion factors will work because they mean exactly the same thing. So therefore, converting first the micrograms to grams, as I did in the second part of the problem here. So now our micrograms are canceling. And now we convert the grams to moles by dividing by the molar mass of mercury. And we get that mercury is an element, so technically the atomic mass. And we get that from the periodic table. Mercury has an atomic mass of 200.59 grams per mole. And so now the grams are canceling. And then now we need to just convert the milliliters to liters. And there are 1,000 milliliters per liter. So now we've got the units that we want, molarity. Molarity units are moles per liter. And we do the math. So did anyone get an answer for this one? You can type it in the chat box. Any answers for that one? So we started out with 16. That's 2 significant figures. So our answer needs to have 2 significant figures. So that we have 8.0 times 10 to the negative 7. Sorry, to the negative 5 molarity. I can write moles per liter, or I can just write my capital M. And that's how you'll see it expressed most of the time, just with the capital M, understood to mean moles per liter. Any questions about number 1? Number 2 is also a molarity-based problem. We're given 2 different molarities, 1.5 molarity and 0.15 molarity solutions of sodium chloride, NaCl. How many moles of solute are present in 500 milliliters of each of these solutions? So we're given molarity, we're given milliliters of 500, which therefore we can easily convert to liters. So 500 milliliters is 0.500 liters. So we know molarity and we know liters, so we can calculate moles. So for the first solution, the moles is going to be 1.5 times 0.5, which gives us 0.75 moles. And then the second one would be 0.075 moles. In each case, the liters cancel. And knowing that the 1.5 molarity, that's 1.5 moles per liter. So therefore, you can see that with the molarity equation being moles of solute per liter of solution, if you know two of those three variables, you can calculate the third. So you could be given moles and molarity and be asked to calculate the number of liters. Or like in this question, we were given molarity and volume in milliliters, and therefore we can use that information to do what we just did, and that's to calculate the moles. Question 3, again, is a molarity-based question. And so two solutions are prepared. The first solution is prepared by dissolving 0.5 moles of sodium chloride in enough water to form 250 milliliters of solution. 250 milliliters is 0.250 liters. And then another solution was prepared by dissolving 0.60 moles of the salt to form 200 milliliters, which is 0.200 liters of solution. Which solution is more concentrated? And so the solution that's more concentrated is the one that will have the greatest molarity, and molarity being moles per liter. So we know the moles for each solution, and we know the liters for each solution. So we need to calculate the molarity for each solution. And so what are the molarities for these two solutions? So solution 1 has a molarity of 2. Solution 2 has a molarity of 3. So therefore, solution 2 is the more concentrated. So you can see the first 3 problems were molarity-based problems, but you can see that they can ask you a variety of different types of questions based on that one single concept. So question 4 is no different. It's a molarity-based question. And so a student's in the laboratory and they have to prepare a 1 liter solution of copper sulfate. And the concentration of the copper sulfate solution must be 2.0 molarity. And so this is how the student prepared the solution. The student placed 40 grams of copper sulfate crystals in a volumetric flask, filled it to the mark with water, and the mark at the 1,000 mil mark. And of course, 1,000 milliliters is equivalent to 1 liter. Did the student make the solution correctly? In other words, was the solution that this student made actually 2.0 molarity? Explain. So we know the student weighed out 40 grams, and we know our little flow chart. See here again, our little flow chart helps us out. We know how many grams that the student weighed out of copper sulfate. So we need to know the molar mass of copper sulfate. We should know how to calculate that at this point. So we take the grams and divide by the molar mass of copper sulfate to get the number of moles that the student used. And then you divide that number of moles by the number of liters of solution that the student made, which is 1, and makes our problem so easy. And then that will give us the molarity of the solution that the student made. And then if that is equal to 2.0, then yes, the student made the solution correctly. If the molarity is not 2.0, then no, the student did not make the solution correctly. So does anyone have an answer to that question? Is the solution 2.0 molarity that the student made? So Ewan says no. What was the concentration that the student made? So Ewan said it was 0.251 molarity. Does everyone agree? So Ewan, you can tell me whether or not the way I'm setting up this problem, you tell me whether or not you set it up the same way. Was your molar mass of copper sulfate 159.6? Okay. So to convert the grams to moles, we divide by the molar mass. And so now we have to then divide the moles by the volume to get molarity. And I get the same, 0.251 molarity. So no, the solution is not 2 molarity. So the student did not make the solution correctly. The student did not weigh out enough copper sulfate. Because the student's solution's molarity is much less than what was needed, that means the solution that the student made was too dilute. And saying it was too dilute means it wasn't concentrated enough. It was only 0.251 molarity. It needed to be 2.0 molarity. So that means the student should have weighed out a whole lot more copper sulfate. Now, if we want to know how much copper sulfate, that's another question that could have been asked. Well, how much copper sulfate should that student have weighed out if 40 grams wasn't enough? Well, if we wanted 2.0 moles per liter to be our molarity of our solution, and then copper sulfate has a molar mass of 159.606 grams per mole, and we want a 1 liter solution. So now the moles cancel. And the liters cancel. So 2 times 159.6. So she or he should have weighed out 319.2 grams. That's how much was needed to actually make a 2.0 molarity solution of the copper sulfate. So that student weighed out a whole lot less copper sulfate than what was required. So that's why the solution was not 2.0 molarity. And so question 5, we want to know the percent or parts per 100 water in the hydrated ionic compound strontium chloride hexahydrate. And so what is the answer to that one? We did calculations for this on last week in our lab. And so to calculate the percent water, you need to take the total amount of water represented in the mole for the molar mass of the hydrate and divide it by the total molar mass. times 100. And this was one of the compounds that was potentially our unknown last week, but it was not our unknown. But in the pre-lab activity, you had to calculate the percent water. And so, anyone have an answer for this one? Anyone have the molar mass for this one? In the last two chapters, after we get through chapter 5, and I'm hoping I can get through as much material in class today and Wednesday as possible before your test. But what's really necessary is that you come to class prepared. And I was expecting for you guys to have answers to these done. And we only have an hour and 15 or hour and 20 minutes twice a week. And I can go through more material with you if you are actively participating in the class with me. If not, that's going to mean that's less material that I'm going to be able to go over. And so it's very important for you to have your calculator during class time and that you're working out the problems and that you read ahead and work a little bit ahead before class so that you are not maybe 100% comfortable with all the material, but that you're comfortable enough with the material before class that you can actively participate in class. And so our strontium is 87.62 grams per mole. And so the total molar mass of the compound is 266.6 grams per mole. Thank you, Gabrielle. Our chlorines, we've got 2 of them. And so that gives us 70.90. And then here's the important parts for the waters. We've got 12 hydrogens, 6 times 2. And then oxygens, we've got 6 of them. That gives you about 96. And that's how we get the total of 266.6 for the total molar mass of the compound. And then the waters make up 96 plus 12.12 of that total hydrate. The water is just the oxygen and the hydrogen components. So this much is the total molar mass of the water. Which is 108.12 grams per mole. That's your total molar mass of water in the compound. And so our percent water is 40.4. Thank you, Gabrielle. And that is found by taking 108.12 and divided by the total molar mass of the compound. The grams per mole units cancel. And you get your 40.4%. And so we talked about solutions as being composed of a solute, which is the substance that gets dissolved, and the solvent, which is the substance that is doing the dissolving. And so most solutions have water as the solvent, especially solutions that we make in a chemistry laboratory. However, you can have a solute other than water. I'm sorry, you can't have a solvent other than water. And so taking a deeper look at solutes, solutes can either be electrolytes or non-electrolytes. Ionic compounds are electrolytes, and they are popular solutes that exist in solutions. So when a salt like sodium chloride is placed in water, it will dissociate into its individual ions. So sodium chloride is composed of a sodium ion and a chloride ion. So for every molecule of salt, NaCl, that dissolves in water, you get 2 separate ions per molecule. And the number of units or ions that dissociate is called the Van't Hoff factor. So sodium chloride has a Van't Hoff factor of 2 because per molecule of sodium chloride that dissolves, you get 2 different ions in solution per molecule of sodium chloride. And the Van't Hoff factor is abbreviated with a lowercase I. So we know that water is polar, and we said that water is polar because of the OH bonds, and the OH bonds being composed of an oxygen and a hydrogen, and the oxygen being more electronegative than the hydrogen, it will carry a partial negative charge versus hydrogen's partial positive charge, and therefore oxygen is drawing more of the electron density in that OH bond towards itself. And therefore, water molecules can hydrogen bond with each other because the partial positive charge on a hydrogen of one water molecule is going to be attracted to the partial negative charge of a neighboring water molecule. So therefore, you'll have these intermolecular forces that we call hydrogen bonds. However, when you place a salt like NaCl in a sample of water, the sodium ion and the chloride ion break apart from each other, and now those ions are free in the water. And so what happens is the salt has its full sodium positive charged ion and its full negatively charged chloride ion. Now the water molecules are going to be more attracted to the sodium and chloride ions than they are to each other. And so now the full negative charge on the chloride ions are going to be attracted to the partial positive charges on the hydrogen atoms on the water molecules. And also, the partial negative charges on the oxygens of the waters are now going to be attracted to the full positive charge on the sodium ion. Now, there's still going to be some hydrogen bonds in that salt water that you've now made by adding the salt to the water, but there are going to be fewer hydrogen bonds. Most of the oxygen and hydrogen atoms on the water molecule are now going to be attracted to the positive charge on the sodiums and the negative charge on the chlorines. And so these are called ion dipole interactions. They are stronger than hydrogen bonds, and therefore they're able to disrupt the hydrogen bonding network in a sample of water. So adding salt to the water, it disrupts the hydrogen bonds between the water molecules because now the water molecules will be more attracted to the salt ions than they are attracted to the partial negative and partial positive charges that exist in neighboring water molecules. And so sodium chloride is a salt, but there are many other salts that contain polyatomic ions, like sodium sulfate is also an ionic compound. But when it dissociates, it will dissociate into 2 sodium ions and 1 sulfate polyatomic ion. And so its Van Hoff factor will be 3. The 2 sodiums plus the 1 sulfate. And so 3 ions will separate per 1 molecule of this sodium sulfate. And so those will also form ion dipole interactions in a sample of water. So, are all ionic compounds soluble in water? The answer to that question is no. There are some ionic compounds that will not dissolve in water. And so here we have a solubility rules table that lets us know whether or not an ionic compound containing a particular type of ion, whether that ionic compound will be soluble in water or not. So if the ionic compound has a metal ion that is either a group 1 metal ion, or if it's the ammonium polyatomic ion, then that ionic compound will be soluble in water, no exceptions. So the group 1 metals are like sodium, that's why sodium chloride, as we just showed, as well as sodium sulfate, those are soluble in water because sodium is a group 1 metal, and all salts that contain group 1 metals are soluble, no exceptions. And so potassium, sodium, lithium, rubidium, cesium, those are all group 1 metals. And then the ammonium polyatomic ion, NH4+. If the ionic compound contains that ion, then that salt will be soluble in water. If the ionic compound contains a nitrate polyatomic ion, then it will be soluble in water, no exceptions. So like lithium nitrate or magnesium nitrate, those are soluble. And the next category are chlorides, and we can also add bromides and iodides to this list. Those are your bromide, chloride, and iodide ions. Most of them are soluble. There are 3 main exceptions. If that iodide, bromide, or chloride, and these, just to note, these are called halides. Iodide, bromide, chloride. If those halides are paired with a silver metal, a mercury metal, or lead metal, then they won't. Then the salt will not be soluble in water. So in other words, magnesium chloride is soluble. But silver chloride is insoluble in water because silver is one of those exceptions. So the key to this solubility table is being able to interpret it. And this is another thing that I'll put on a data sheet that I'll compose for you, and I will post under the course content tab in eLearn, and I'll also email it to you. This is something that you would want to have next to you when you're taking your next test to refer to. As far as sulfates have the sulfate polyatomic ion. Most sulfates are also soluble, with these exceptions. If the sulfate is paired with a strontium, barium, lead-2, or silver-1 metal cation, then it is not soluble. So potassium sulfate is soluble, whereas barium sulfate, barium being an exception, would not be soluble. For carbonates, we can also put phosphates in this category. Phosphates contain the phosphate polyatomic ion. Carbonates contain the carbonate polyatomic ion. They are mostly insoluble, but there are a couple of exceptions. If a carbonate or a phosphate polyatomic ion is paired with the group 1 metal or the ammonium cation, then that ionic compound would be soluble. So for example, sodium carbonate is soluble because sodium is a group 1 metal, so that'll be an exception to the insolubility. However, calcium carbonate is insoluble. And then hydroxides, those are OH minus ions, and sulfide is S2 minus. So if an ionic compound contains the hydroxide polyatomic ion or a sulfide monoatomic anion, then that ionic compound will be mostly insoluble, except if it contains a group 1 metal or the ammonium ion. So potassium hydroxide, potassium being a group 1 metal, is soluble, but strontium hydroxide is insoluble. And so this table is very useful for determining whether or not an ionic compound will dissolve in water, meaning it's soluble, or if it does not dissolve in water, meaning it is insoluble. Ionic compounds can react with each other. When they react with each other, they do a double displacement. In other words, they exchange ions with each other. And then you'll get two products. One of the products, you'll have two different situations. Either both of the products will dissolve in water and therefore form what we call aqueous solutions, or only one of the products will dissolve in water and the other product is insoluble and therefore forms a solid, which we call a precipitate. The solid precipitate product is not soluble in water. The other product will be soluble and therefore will form an aqueous solution. So if reacting two ionic compounds together produces a solid precipitate, then that means that the double displacement reaction is also categorized as a special type of double displacement reaction called a precipitation reaction. So when silver nitrate reacts with sodium chloride, what's going to happen is the ions will exchange. And so silver is paired with nitrate. But then think of it as it's going to break up with the nitrate and get a new partner. And its new partner is going to be the chloride ion. So it's going to steal sodium's partner. And then the same thing will happen on the other end of things. Sodium now doesn't have a partner because silver stole its partner. So its new partner is going to be silver's old partner, nitrate. So it's just exchanging ions. So our products are going to be sodium nitrate, and silver chloride. So the question is, are both of these soluble in water? If so, they both will be aqueous solutions. But if one is an aqueous solution and the other is a solid precipitate, then which one? Which one is the solid? And so we use our solubility rules to answer that question. So sodium nitrate, would it be soluble in water? And if so, which rule? The first two rules. Sodium nitrate contains sodium, a group 1 metal, so it has to be soluble, no exceptions. And it also contains the nitrate polyatomic ion. So therefore, again, it is soluble, no exceptions. So if it's soluble, that means it's an aqueous solution. What about silver chloride? Is it soluble in water? We need to look at this rule for chloride. Most of them are. Are there any exceptions? Yes, if it's paired with silver, mercury, or lead. There's silver paired with the chloride. So is silver chloride soluble, or is it a solid precipitate? AgCl is not soluble, so it will be a solid precipitate. So that's how you take a look at two ionic compounds reacting together, do the exchange of ions, write your two products, and then consult the solubility rule table to see if one of those products is a solid precipitate. And so I stated earlier that ionic compounds are electrolytes. An electrolyte is a solution that has dissolved ions in it. And therefore, it is a solution that conducts electricity. So in order for that solution to be able to conduct electricity, it has to have free ions in that solution. If you dissolve sugar in water, that's going to be a non-conducting solution because a sugar solution is a non-electrolyte. So it does not conduct electricity. Sodium chloride, however, dissolved in water, is conducting because sodium chloride solutions are electrolyte solutions. And so the sodium chloride, when placed in water, it dissociates into the sodium ion and the chloride ion. So you have these ions free in solution with their charges, and therefore they're able to conduct an electrical current. Like this picture demonstrates, if you place these electrodes in a sugar solution, the light bulb does not come on because the sugar solution is unable to conduct an electrical current because it's a non-electrolyte. And therefore the light does not come on. However, if you place the electrodes in a salt solution, which is an electrolyte, the light bulb comes on. So therefore, those free sodium and chloride ions are able to conduct an electrical current. So an electrolyte can either be a strong electrolyte or it can be a weak electrolyte. Sodium chloride, because it contains a sodium ion and all group 1 metal ions are soluble. So sodium chloride is soluble in water, and we know that from experience as well. And so therefore it dissolves completely in water. And so that makes it a strong electrolyte. So dissolving 100% of all molecules that you place in a given volume of water will dissociate into those sodium plus and Cl minus ions. So strong electrolytes are most ionic compounds. As we saw in the solubility rules table, some ionic compounds are not soluble in water. They don't dissociate completely. Also, strong acids and strong bases. They are also strong electrolytes. And we'll talk about strong acids and strong bases on Wednesday. Weak electrolytes, they partially dissociate into ions, but some of the full intact molecule will remain, but partially dissociating into ions will occur. So therefore, they're classified as weak electrolytes because they only partially dissociate into ions. And so therefore, substances like tap water, weak acids, and weak bases are classified as weak electrolytes. And we'll also talk about weak acids and weak bases on Wednesday. And so if you have a compound that dissolves in water, it doesn't necessarily mean it's an electrolyte. Like sugar, it dissolves in water, but it is a non-electrolyte because it stays as full intact sugar molecules when it dissolves in the water. And so therefore it does not dissociate at all into ions. So sugars are non-electrolytes, also alcohols, purified water like bottled water or water that you filter through a semi-permeable membrane filtration system. That will also be pure water, meaning it's been either deionized or distilled. And then non-soluble ionic compounds are also considered non-electrolytes. And so one of the rules that we learned previously in a lab that we did this semester in judging whether or not water will be dissolved or miscible with ethanol, for example. If both of the substances are polar, then they will dissolve in each other based on the simple rule like dissolves like. So a polar compound like ethanol will dissolve in a polar solvent like water. A nonpolar compound like other nonpolar substances like gasoline. But oil, being nonpolar, will not dissolve in water. So for the next set of questions, number 1, completing the table with the ionic compound names and answering the question, yes or no, is it soluble in water? And so when you're answering questions whether or not a substance is soluble in water, take a look at the cation, take a look at the anion, and then consult the solubility rules table to see what the solubility rules table tells you about one or both of those ions. So lead nitrate contains the nitrate polyatomic ion. The first 2 rules are very easy to memorize. If it's a group 1 metal, or if it's the NH4 plus cation, a part of the ionic compound, then it's soluble. If the ionic compound contains the nitrate polyatomic ion, it's soluble. So therefore, lead nitrate contains the nitrate polyatomic ion. And for these first two rules, there are no exceptions. So it doesn't matter what nonmetal a group 1 metal is bonded to. By there being a group 1 metal as your cation, it's soluble. Same thing with the nitrate polyatomic ion. Doesn't matter what metal cation that is bonded to in the ionic compound. If the nitrate poly is present, no exceptions. So therefore, we can answer yes, because this contains the nitrate polyatomic ion. It's soluble. And this is lead nitrate. And lead is a transition metal, so I've got to put my Roman numeral, lead 2 nitrate. Here we have calcium sulfate. Based on the solubility rules table, will this be soluble in water? So you've got a sulfate polyatomic. They're most soluble, except for if the sulfate is paired with either of these four. So is calcium sulfate soluble in water? Yes or no? Soluble, except if paired with metal or silver metal. So does calcium qualify as an exception? So Madison, is calcium soluble? You're saying that calcium sulfate is soluble in water, or no, it's not soluble in water? Yes, it is soluble in water. What about aluminum hydroxide? What does the solubility rule table tell us about hydroxides? They are mostly insoluble, except for if the OH minus polyatomic ion is paired with a group 1 metal or ammonium. And so I agree, Ewan, it is not soluble. What about silver bromide? Bromide is one of those halides, like chloride, iodide. So what about the halides? They are mostly soluble, except for silver. Bromide be soluble?
Yes.
Is silver an exception? They're mostly soluble, except
Yes.
with silver, mercury, or lead. So is it soluble or not soluble? Very good, Madison, not soluble. You need to, I would suggest really study this table. Make sure you're interpreting it correctly. So for the halides, including chlorides, bromides, and iodides, they are mostly soluble, except if those anions, they have negative charges, chlorides, bromides, and iodides. So in the ionic compound, they're paired with a positively charged metal cation. And if they are paired with a silver metal, mercury 1 metal, or a lead 2 metal, that's an exception, which means that they're not soluble if they have one of these metals paired with a halide. So silver bromide makes the bromide insoluble. Any questions about number 1? And so we did the double displacement reaction example earlier, in which you have the exchanging of partners. So you have your metals switching partners with each other. So in this first one, sodium is paired with sulfide. It's going to get a new partner, which will be chloride. Magnesium is paired with chloride, but once chloride goes away with sodium, its new partner is going to be sulfide. So your products are sodium chloride and magnesium sulfide. So the question is, are both of these soluble in water? And therefore we need to put AQs in the parentheses, or is one of them soluble and one insoluble? So we have to, again, consult our solubility rule table. Well, if we memorize the fact that if a salt has a group 1 metal cation, like sodium, potassium, so on and so forth, then it's soluble, no exceptions. So we can say, yes, the sodium chloride is soluble. What about the magnesium sulfide? What does the solubility rule table tell us about the sulfides? They're mostly insoluble, except if the sulfide is paired with a group 1 metal or the ammonium cation. Magnesium is a group 2 metal, not a group 1 metal. So is MgS soluble or insoluble?
Insoluble.
Very good. So it's a precipitate. It's solid. So see how you use the solubility rule table to take a look at the products of a double displacement reaction, and you can determine whether or not both of the products are soluble, or if only one of them are, and the other is a solid precipitate. So I'm going to leave the last two for you guys to do before Wednesday. For number 3, identify these different products as strong electrolytes, weak electrolytes, or non-electrolytes. Well, glucose is a sugar. So what would it be? Will it be able to conduct an electrical current?
No, and it will be soluble.
Correct. It is soluble in water, but it doesn't produce any ions in solution, so that will make it a non-electrolyte. 1-propanol is an alcohol. Alcohols are also non-electrolytes. They dissolve in water. We proved that in one of our labs early in the semester when we said that ethanol and water are miscible in each other. But alcohols do not produce any ions in solution, so it cannot conduct an electrical current. So therefore, it is a non-electrolyte. The next one is an ionic compound, KNO3. But just because it's an ionic compound, it doesn't necessarily mean that it's a strong electrolyte. It's only a strong electrolyte if it's soluble in water. So if you're trying to judge whether or not an ionic compound is a strong electrolyte, consult the solubility rules table to see if it's soluble in water. And if it's soluble in water, then it is a strong electrolyte. And we've looked at nitrates as well as group 1 metals. We know that rule, that they are soluble in water, no exceptions. Tap water, however, contains ions. It's not pure. So tap water is a weak electrolyte. But Dasani bottled water it should be pure water. So therefore it's a non-electrolyte because it doesn't contain any ions. HCl is a strong acid. So therefore all strong acids and strong bases are strong electrolytes. However, acetic acid, which is found in vinegar, is a weak acid. So it is a weak electrolyte. And we're going to talk in great detail on Wednesday about strong acids, strong bases, weak acids, and weak bases. And acids and bases are the subject of our lab this week. So let's get a little introduction into acids and bases before we go for the day. So acids, they have been historically defined as having specific physical properties, such as having a sour taste, and they have the ability to have certain chemical properties, like being able to change the color of an indicator by reacting with it. And it has also been proven that acids react with carbonates. And also, when studying acids, acids always will contain a hydrogen ion, H plus. H plus is formed from the hydrogen atom. After the hydrogen atom, which has only one electron, when it loses that one electron, it becomes H with a +1 charge. And therefore it becomes an ion. And because now it has no electrons, but it still has its one proton, H plus hydrogen ion is often referred to as simply a proton. And so one way to define an acid is that it's a substance that has the ability to release hydrogen ions in aqueous solution. And that's called the Arrhenius definition of an acid, named by the scientist who made that observation and therefore that definition. So in other words, an acid like hydrochloric acid, HCl, when placed in solution, it will dissociate into its two ions, one of them being the hydrogen ion. So therefore, by that definition, you classify HCl as an acid because it releases an H plus ion in solution. And when we see the dissociation of the HCl into its two ions, you have the forward arrow. And that means that the HCl dissociates completely into its two individual ions. That is what makes it a strong acid. Strong acids dissociate completely into their individual ions. H plus ions are very, very strong, therefore very not stay in ionic form very long because they want to react with something. They're very reactive. So they're going to react and attach themselves with something else, like water molecules. For example, if we're dealing with aqueous solutions, meaning that we're putting the HCl in water. So when you dissolve HCl in water, HCl is going to donate its H plus ion to water. And so when the H plus ion gets donated to the water molecule, it forms a new product called the hydronium ion. And that's the Bronsted-Lowry definition of an acid. It is a substance that's able to donate a proton. So HCl reacting with water is going to donate its proton to the water, and that's how H3O plus, the hydronium ion, is formed. The Cl minus ion is your other product. The hydronium ion is sometimes simply written as H plus. Therefore, these two reactions are essentially the same. So it's understood to mean the same thing as H3O plus. So here you have the Lewis structure of the hydronium ion, H3O+. You got the central oxygen atom bound to the 3 hydrogens. And then your number of valence electrons, each hydrogen has 1. And then the oxygen, there's 1 of them in group 6. And then you have to subtract 1 for that +1 charge. That means that 1 electron was lost. So that gives you 8 total valence electrons, which are shown here. And so we said that HCl is a strong acid because it dissociates completely into its ions when you place it in water. And so here is a list of the other strong acids. There are 7 total. So if an acid is not in this table, that means it's not a strong acid. It's a weak acid. So like acetic acid, which we mentioned earlier, it's in vinegar. It's not on this list. So therefore it has to be a weak acid. So the first 3, these are called binary acids because they consist of only 2 types of elements or 2 types of atoms. HCl is a hydrogen atom and a chlorine atom. HBr, hydrogen and bromine, so on and so forth. So that's why they're called binary acids. The last 4 on this list, these are called oxo acids because they have 1 or more oxygen atoms in their formula. So I've got the names of them shown here in the table as well. So to name binary acids, you always use the prefix hydro. The hydro prefix takes care of the hydrogen. And then the other atom, which is your nonmetal, chlorine, you drop the ending of chlorine and you replace it with ic acid. So HCl is hydrochloric acid. And then for the oxo acids, they're based on their polyatomic ion. So ClO4 minus, for example, is the perchlorate ion. And so the acid HClO4, you drop the 8 ion and you replace it with ic acid. And so that's how you name the oxo acids. ClO3 minus is the chlorate ion. So the acid HClO3 is chloric acid. So again, you drop the 8 and the word ion and replace it with the suffix ic and then the word acid. So in addition to part 2 of the notes, I asked you to finish up question 2, parts B and C. So we'll discuss the solutions to those first thing on Wednesday. And then in part 3 of our notes, I want you to take a look at questions 1 and 2. For question 1, we're asked to provide a balanced chemical equation that shows the release of a proton H+ in water. Also provide an equation that shows the formation of a hydronium ion. So for HBr, it's going to break apart into H+, and Br minus. And then my second equation that shows the formation of the hydronium ion, I actually show it reacting with the water. The proton, H plus, is going to get donated to the water to form H3O plus. And I still have my bromide ion as well. So I'm going to let you finish B and C, doing those the same way I did part A. And then question 2, list at least 5 foods or beverages that are acidic. Well, one that I know I partake a lot of is coffee. Coffee is acidic. And drinking lots of acidic beverages can have the long-term effect of reacting with the enamel on your teeth. So therefore, it's important to make sure your toothpaste has fluoride in it, because the fluoride ion, F minus, in the toothpaste, it will react with the acids in the stuff you drink instead of those acids reacting with your tooth enamel. So therefore, the fluoride stops the acid from reacting with your tooth enamel because the fluoride reacts with it and therefore helps to neutralize those acids. So that's why it's so important to brush with the fluoride toothpaste. So coffee is definitely one of them, and I'll let you think of 4 more. So we'll stop lecture at that point today, and we'll pick back up in part 3 of chapter 5 notes on Wednesday. And we'll also give you an introduction to this week's lab, which is on acids and bases. And so if you have any questions, just feel free to ask those at this time. If not, I will see you on Wednesday.